Two people sit down to the exact same breakfast. Matching eggs, matching bowls of yogurt, 20 grams of protein on each plate, eaten within an hour waking. One of them is 35 years old. The other is 65. Inside the younger person, the muscle detects the incoming protein and launches into a strong building response, a wave of construction that continues for the next 3, 4, even 5 hours. Inside the older person, that same meal barely changes anything. The muscle registers that food has arrived but does very little with it. Same eggs, same amino acids, the same delivery through the same bloodstream into muscles that, from the outside, appear as though they should function in much the same way. Yet, one muscle starts building while the other barely reacts. The protein reached both bodies completely. The muscle at 65 simply looked at the identical delivery and submitted a smaller work order than it would have submitted 20 years earlier. Here is what almost nobody explains clearly about getting older. Your muscle did not lose the machinery required to build itself. Every major component is still there. The system can still read protein, activate its building pathway, and respond when the right signal arrives. What changed is the strength of the push needed to activate that system. The trigger point gradually moved higher over the years, and the breakfast that once crossed it without difficulty may now land just below it. You are eating the food, your muscle is receiving the amino acids, and the signal is arriving, but is falling slightly beneath the level needed to begin substantial construction. The threshold moved. The protein on the plate did not. That is the central mystery this video will unravel. Your muscle is still capable of doing its job. The building machinery, the signaling systems, the pathways, all of them remain available and functional. The real question is why the same steady input now creates a smaller response. What raised the amount of protein or signal your muscle needs to cross that line? And what is missing from your morning meal that can help push the signal back over the top? So let me build the answer piece by piece, because these factors stack together, and each one can raise that threshold a little higher than the one before it. Start with something about your nighttime hours that you have probably never thought about in terms of muscle biology. Sleep is a fast. Your last meaningful protein delivery usually arrives with dinner, perhaps around 7 o'clock or 8 o'clock in the evening. The next delivery does not show up until breakfast, around 7 o'clock or 8 o'clock the following morning. That creates 10, 11, and sometimes 12 hours without a new supply of dietary amino acids. It is the longest uninterrupted gap of your entire day, and it happens while you are asleep, completely unaware of the process. During those hours, your muscle does not simply switch off and wait for morning. It continues breaking down its proteins at a normal background rate, just as it does throughout the day. Old, damaged, or worn-out components are dismantled, and the amino acids released from that process are redirected to other parts of the body. They can support immune cells, enzymes, organs, and countless other systems that continue operating while you sleep. Breakdown continues. Building, however, slows dramatically because there is very little new material arriving to support it. Hour after hour, the muscle operates at a small deficit, breaking down slightly more protein than it replaces. By the time you wake up, the available amino acids circulating in your blood have generally fallen toward one of their lowest points of the day. Your muscle has spent 10 or 12 consecutive hours in a period where the balance has shifted away from new construction. That makes the first meal of the morning far more important than the simple word breakfast suggests. It represents the first major opportunity in nearly half a day to stop that overnight loss and move the balance back toward building. Notice how the timing works, because the difference is surprisingly large. The fast before breakfast is usually the longest fasting period your body experiences all day. The gaps between your other meals might be 4 to 6 hours, while the overnight gap can stretch to 10 or 12 hours, roughly twice as long. So the longest uninterrupted period with little incoming protein occurs immediately before the meal that many people make surprisingly light, perhaps a piece of toast, a small pastry, or a cup of coffee. The deepest gap of the day can therefore sit directly underneath one of the smallest protein servings of the day. Keep that picture in mind, because it is about to collide with a second problem. And the second problem is the one that gradually raises the bar. That problem has a name: anabolic resistance. It sounds technical and somewhat intimidating, So let me give you the picture first, because the idea itself is simple and something you already understand. Think about a doorbell. For years, the doorbell responded to the lightest touch. A gentle press was enough, and the chime carried clearly through the entire house. Then, slowly, the button began to stiffen. The wiring behind it became less responsive. The same gentle press you had used for years stopped producing a sound. The doorbell itself was not necessarily broken. The chime still worked if you pressed the button firmly enough. What changed was the amount of pressure required before the circuit would close, and the signal could travel through the system. The touch that once was enough now falls just short of the point where the bell agrees to ring. Your muscle has a button that works in much the same way. Think of it as a master switch that decides, meal by meal, whether to wake the construction crews or leave them inactive. It responds to a specific chemical signal in the bloodstream, an amino acid called leucine, which acts like a messenger announcing that protein has arrived and the raw materials for construction are available. When enough leucine reaches a switch, it activates, and muscle protein synthesis rises for several hours. When the signal is too weak, the switch remains largely inactive, and the meal can pass through without fully engaging the building machinery. At 35, that switch was highly responsive. Around 20 to 25 grams of protein, containing roughly 2 to 2.5 grams of leucine, could provide enough pressure to activate it and produce a strong building response for hours afterward. That was a gentle touch on a younger doorbell. It worked, and it worked with relatively little effort. By 65, the button has become less sensitive. 25 grams of protein, with around 2 grams of leucine, may press against the switch while producing only a modest reaction. A response that once sounded like a full roar can become much more like a quiet murmur. To produce the kind of building response that younger muscle could achieve with a smaller serving, older muscle may need something closer to 35 or 40 grams of protein in one meal, supplying roughly 3 to 4 grams of leucine. This reflects a measured physiological shift. The muscle-building response tends to rise only after the protein dose moves well beyond the amount that was sufficient for younger muscle, a difference that researchers such as Cuthbertson and colleagues have examined directly in older adults. The pressure required to ring the bell increased. The bell itself did not disappear, and the basic machinery remained in place. It helps to understand what actually becomes less responsive inside that switch, because the switch is not one single component. It is a short sequence of molecular parts that have to work together. When leucine arrives, it does not simply flip the switch by itself. It first has to overcome a braking system. In resting muscle, a group of nutrient-sensing proteins helps keep the signaling pathway restrained until enough leucine is present to release that inhibition. Only after that restraint is reduced can the main pathway become fully active and send the building message farther down the line. In younger muscle, a relatively modest rise in leucine can provide enough of a signal to release that brake. In older muscle, the response will be less sensitive, and the downstream signaling pathway may also respond less strongly, meaning the same increase in leucine produces a smaller overall effect. Researchers have traced this reduced response through the signaling pathway itself, following the molecular relays below the initial nutrient signal, and finding that older muscle can show a weaker activation pattern after the same protein dose. The messenger may arrive with the same message, but fewer of the relays farther down the line respond with the same intensity. So the leucine is still reaching the muscle. The issue is what happens after it arrives. The muscle has become less responsive to a signal it once handled more efficiently, and this reduced sensitivity is not necessarily an isolated feature of muscle. Aging often involves changes in how strongly different biological systems respond to their signals, with some receptors, sensors, and pathways requiring a stronger stimulus to produce the same result they once produced with less. In that sense, aging can be viewed partly as a story of changing thresholds. Nerve endings that once reacted quickly to a small stimulus, sensors that once responded to modest pressure, and cellular switches that once activated after a relatively light chemical signal can all become less responsive over time. The muscle's leucine-sensitive pathway is another example of that broader pattern. The button is still there, the machinery still works, but the press required to activate has become stronger, so the bar has moved higher. And that brings us to the question that actually matters tomorrow morning. What does your normal breakfast put against that less sensitive switch? There is also a particular problem with the timing that deserves attention before we start counting grams. The overnight fast has already left you without incoming protein for 10 or 12 hours. Of all the meals you eat, breakfast begins with the largest overnight gap already behind you, leaving the muscle in a position where a strong protein signal could be especially useful for shifting the balance back toward construction. It is the meal with an unusually large opportunity to correct the overnight deficit. Yet for many people, it is also the meal with the least protein. Miss the protein target at dinner, and you have missed one ordinary opportunity during the day. Miss it at breakfast, and you may leave the largest gap of the day only partially addressed for several more hours until lunch. The morning is therefore a time when a subthreshold protein meal can matter more than people realize, and that is exactly when a plate of toast often becomes a default choice. Breakfast can be one of the meals where adequate protein matters most, yet it is also one of the meals where protein is frequently overlooked. So, let us add everything together honestly. Consider the breakfast that many adults over 60 might actually eat. 2 slices of toast may provide only around 2 or 3 grams of protein altogether. Butter contributes essentially no meaningful protein. Coffee with a small amount of milk might add another gram or 2. A little fruit on the side may contribute less than a gram. Put the entire plate together, and you may end up somewhere around 4 to 7 grams of protein. And when you look at how little leucine is contained in that amount, you are dealing with only a fraction of a gram, perhaps around 0.3 to 0.5 grams. Set that amount beside the switch. Older muscle may need roughly 3 to 4 grams of leucine to produce a strong response, typically coming from a meal containing around 35 to 40 grams of high-quality protein, while the toast-based breakfast provides only a small fraction of that amount. It is like pressing the doorbell with barely a tenth of the force required for the bell to respond. You ate a genuine breakfast. You chewed the food, enjoyed it, and left the table feeling satisfied. But down at the cellular switch, the signal was barely strong enough to register. The construction crew remained largely inactive during the very part of the day when your muscle had just come through its longest period without incoming protein, and the meal that followed supplied the weakest protein signal. There is another part of this calculation, and it is hidden in the way many people distribute their protein throughout the day. Picture the familiar pattern: a small breakfast, a moderate lunch, and then a large dinner, perhaps a generous portion of chicken, fish, or steak carrying most of the day's protein in one evening meal. On paper, the daily total may look perfectly adequate, perhaps even impressive. Inside the muscle, however, the timing can be far less effective. Here is a reason. That master switch has a practical limit to how much building activity it can generate from one meal. Give around 40 or 50 grams of protein at dinner, and assuming the meal is well digested and the protein is high quality, the muscle-building response can be strongly stimulated. Add another 80 or 100 grams in the same sitting, however, and the muscle cannot simply convert all of that additional protein into proportionally more construction. Once the response has reached its effective ceiling, extra amino acids can be oxidized for energy or directed toward other metabolic needs rather than creating another separate building window. The giant dinner therefore pushes far beyond a switch that has already been activated, while the morning muscle received too little of the signal to activate the process in the first place. One meal is far above the line, while another remains far below it. Across the entire day, the switch may have crossed its effective threshold only once. Think about what the muscle actually detects. It does not see the number printed on your nutrition label, and it cannot look at your daily protein total and decide that everything is fine. It responds to individual protein opportunities, one meal at a time, essentially asking a simple question each time. Did this meal provide enough of the signal to activate the building response? If you arrange your protein so that only dinner clears the threshold, then dinner is the meal that provides the strongest building stimulus, while breakfast and lunch remain below the level needed for a full response. And this creates an important consequence. 2 people can consume exactly the same number of grams of protein over 24 hours and still receive different muscle-building benefits, simply because those grams were distributed differently. Divide the protein into 3 or 4 meals that each provide a strong enough stimulus, and the muscle may receive 3 or 4 separate opportunities to activate its building machinery. Put most of the protein into one enormous evening meal, and you may create only one major opportunity. Making that one serving larger cannot automatically purchase a second building window, because once the response is already near its effective ceiling, additional protein does not simply restart the entire process. The total protein can be identical in both cases, yet the number of times a muscle receives a meaningful building signal can be dramatically different. That number of successful signals is far more relevant to the muscle than the daily gram total sitting on a spreadsheet. Keep the entire picture in view now and connect the pieces. The overnight fast lasts 10 to 12 hours. The older muscle has a higher threshold for a strong protein response, potentially requiring something closer to 35 to 40 grams of protein in a meal, while the typical toast-based breakfast may provide only 4 to 7 grams. The arithmetic makes the problem easy to see, and that leads to the question that determines where we go next. Is protein by itself enough to fix the problem if you simply consume more of it at the right time? Or is your muscle waiting for another signal, something that no food can provide regardless of how much protein you put on the plate? The answer is that it is waiting for another signal. And this is the point where the entire problem begins to look different. Protein was never the complete answer by itself. That master switch responds to two major inputs, and the strongest response occurs when both signals arrive together. The first is a chemical signal you already know, leucine and other amino acids appearing in the bloodstream and communicating that fresh building material has arrived. The second signal is mechanical. It comes from the physical tension created when a muscle is actually used, challenged, contracted, and required to work against resistance. That mechanical tension tells the body that this particular tissue has a reason to be maintained and strengthened. The chemical signal says the bricks have arrived. The mechanical signal says this is the exact place where those bricks are needed. In that sense, the switch acts almost like a coincidence detector. It responds most effectively when both signals appear within a useful period because together they provide the information the muscle needs. New raw materials are available, and this tissue is experiencing a genuine demand for greater capacity. There is a clear biological reason for this cautious system. Building muscle requires substantial energy and resources, and producing new tissue that the body does not actually need will be an expensive investment with little return. So the system looks for evidence from both directions before committing heavily. The chemical signal provides the materials, while the mechanical signal provides the reason, and the muscle essentially insists on proof of both before it spends significant resources on construction. Materials without demand may simply represent a passing meal that the tissue has no immediate reason to use. Demand without materials cannot produce new tissue either. Only when both arrive within the same useful window does the body receive enough evidence to justify the energy and resources required for construction. Give the muscle protein without any meaningful tension, and it is like delivering a pile of bricks without providing an address. Some of those materials may be used for other purposes, but the full building order is never issued. Now picture someone who does everything correctly with food, but does nothing physically afterward. They eat 35 grams of quality protein at breakfast, bringing leucine comfortably into the range needed to stimulate the pathway, and then spend the next 4 hours sitting in a chair. One signal is strong, while the other is almost completely absent. The coincidence detector receives only half the message and produces a limited building response, real but much smaller than it could have been. The materials arrived. The demand that would have directed those materials towards stronger muscle never appeared. Now imagine the small change that alters the outcome. Keep the same 35 grams of protein, but sometime during that morning, place a little genuine resistance on the muscles. Perform several slow sit-to-stand from a chair. Push firmly against the wall. Carry a moderately heavy bag across the room and back. Nothing that would impress an athlete, just enough honest resistance to require the muscle to produce force. Now both signals arrive within the same general window. The materials are available, and the tissue has been given a reason to use them. The system receives a combined message, activates the building machinery more effectively, and protein that might otherwise have produced only a limited response can now contribute much more strongly to the process. Here is why this pairing becomes especially important with age. Both thresholds can change together, with the mechanical requirement becoming more demanding alongside the chemical one. The older muscle may need a stronger nutritional signal and a stronger mechanical stimulus. Both systems can become less responsive to related aspect of aging, meaning both may require clearer evidence than they did earlier in life. At 35, you could sometimes be less precise with one signal because the other was easier to achieve. At 65, the muscle may respond better when both signals are deliberately provided, with both reaching a sufficient level before the body commits substantial resources to new construction. Miss either one, and the response can become much weaker. That leads to a more serious question. What happens to a muscle that spends years, morning after morning, receiving a signal that repeatedly falls below the effective threshold on both sides at once? The answer is gradual, and it has a name you may have heard many times without ever seeing the mechanism behind it. Sarcopenia, the age-related loss of muscle mass and function. Muscle loss generally becomes more noticeable with advancing age, with estimates varying considerably depending on the population, measurement method, and definition used, and the decline often accelerates later in life. More importantly, the loss does not necessarily occur evenly across every muscle fiber. Fibers capable of producing high force and rapid movement can become particularly vulnerable, affecting abilities such as standing up quickly, recovering from a stumble, climbing stairs, or reacting when balance suddenly shifts. There is a reason those fibers can be affected so strongly. Skeletal muscle contains different fiber types with different roles. Slower fibers are well suited to posture and prolonged, lower-intensity activity, continuously contributing to steady movement and stability. Faster fibers are recruited when the body needs greater force or speed, such as rising quickly from a chair, stepping out to regain balance, or producing a sudden, powerful movement. They tend to become involved when the required effort crosses a higher demand threshold. A lifestyle dominated by very gentle, low-load activity may rarely provide a strong reason to recruit them, and a fast fiber that is almost never challenged receives a weaker mechanical signal than a fiber regularly exposed to demanding movement. The tissue specialized for power can therefore become the tissue most easily neglected when daily activity becomes less challenging. Watch those power-producing fibers become smaller or less capable, and you are seeing the biological consequences of reduced demand play out in physical form. This decline connects directly to the pattern we have been building. As the years pass, the stimulus required to maintain and develop muscle can become harder to achieve, while typical dietary patterns and everyday physical demands may become less challenging rather than more challenging. The required signal rises while the delivered signal can fall. Eventually, the two can move farther apart, leaving some muscle fibers repeatedly below the level of stimulation needed to maintain their previous capacity. A muscle fiber is metabolically expensive tissue. The body has to spend energy and resources to maintain its structure, repair damage, and preserve its function. If the system repeatedly interprets a particular capacity as unnecessary, maintaining the same amount of tissue becomes harder to justify. Over long periods, fibers that receive too little stimulation can shrink. Their motor connections can also change, and surviving motor neurons may sometimes expand their territories by connecting with fibers that have lost their original nerve supply. This can create larger motor units and contribute to a loss of the fine control that younger muscle once had. The result is not simply a smaller muscle. It can become a muscle that produces less force, reacts more slowly, and has greater difficulty making the rapid, precise corrections that help keep the body stable when walking, turning, or recovering from an unexpected shift in balance. And there is one more quiet pressure worth understanding, because it reinforces this entire below-threshold cycle from the inside. Building and maintaining muscle requires real energy. Every new strand of muscle protein has to be assembled, repaired, and maintained, and that construction process demands resources that the body carefully manages. On energy, the muscle cell has to spend resources from its own internal power systems. The cellular energy currency that drives those processes can also become harder to maintain with age as the efficiency and capacity of the systems producing it change over time. So even when a muscle receives enough protein and enough mechanical stimulus, the construction process can still be influenced by whether the cell has sufficient energy and metabolic capacity to carry out the work. The nutritional signal, the mechanical signal, and the energy available to act on both can all change with the passing years. It is rarely a single threshold working against you. More often, several small changes quietly compound one another. None of that long-term muscle loss is caused by breakfast alone, and it would be misleading to suggest otherwise. Hormonal changes influence the same process, as do daily activity levels, inflammation, overall nutrition, recovery, and the energy systems inside the muscle cell that support the building work itself. The body considers all of these factors together when deciding how much tissue to maintain and how much new tissue to build. But breakfast is one of the inputs on that list you can change as soon as tomorrow morning without needing a prescription, expensive equipment, or a gym membership. A muscle that repeatedly receives too little protein and too little mechanical challenge is effectively receiving a consistent message of low supply and low demand. Expensive tissue weak justification. Over time, that repeated message can contribute to the gradual reduction in muscle size and function. And once you understand that logic, the direction of the solution becomes much clearer. If the problem is a signal repeatedly landing below a threshold that has become harder to cross, then one practical strategy is to make the signal strong enough to cross it. That brings us to the final practical question, the one you have been waiting for since we started with that plate of toast. What actually gets the signal over the line? The answer is more measurable than you might expect because leucine, the amino acid involved in activating the muscle-building pathway, appears in fairly predictable proportions depending on the protein source. Many animal proteins, including eggs, dairy, meat, and fish, as well as soy, contain roughly 8 to 10% leucine by weight of their protein, while many other plant proteins tend to contain somewhat less, often around 6 to 7%. That simple difference allows you to estimate the size of the nutritional signal. Take the grams of protein in a meal, consider the approximate leucine content of the source, and you can get a rough idea whether the meal is likely to provide a strong enough amino acid signal. A commonly discussed target for older muscle is around 3 grams or somewhat more leucine in a meal, with the exact amount depending on the person, the protein quality, and the overall meal. That is why a serving in the neighborhood of 30 to 40 grams of high-quality protein can become useful when trying to create a strong response. Now run the typical toast breakfast through that calculation, and the limitation becomes obvious. If the meal contains only around 4 grams of mixed protein, much of it coming from grains with lower leucine proportion, the total leucine may amount to only a small fraction of a gram, far below the amount needed for a strong anabolic signal in older muscle. Now change the plate. 3 eggs and a serving of Greek yogurt can provide roughly 30 grams of protein, with a leucine content that may approach the range needed for a meaningful signal. Add a little more protein, such as milk or a serving of whey, and the same basic breakfast can move comfortably into a stronger range. The food itself remains completely ordinary. Nothing exotic is required. The difference is that the plate has been assembled to provide enough of the signal, and now you can see what enough means in actual grams rather than vague advice to simply eat more protein. Your muscle has been responding to this arithmetic the entire time. You simply were never shown the calculation. There are also a few practical cautions that follow directly from it. Collagen, the protein found in bone broth and many supplements, is relatively low in leucine